So I would like to start where we ended last time. So last time we had a look at BitTorrent and how it worked and how you use the trackers and torrents to keep informed about the peer set which is in the swarm and with whom you might exchange chunks. It's very robust and very effective protocol, so didn't change in the last 8 years too much. So it's quite well suited and very optimal at the end. So let's see, but what kind of concerns? So why is it not the end of the road? So what kind of concerns do we still have? And one of the concerns that remains with peer-to-peer and with BitTorrent is that in the recent years, so 2008 up to 2009, peer-to-peer was dominating the overall internet traffic. So here in this picture, for example, you see this is a measurement by the IPOC company, which are doing some internet measurements, and they are showing that the blue color in this picture is peer-to-peer, and in Africa it's 66%, in America and Europe 70%, Germany 50%, so it's quite a lot of peer-to-peer traffic in the internet. And out of the peer-to-peer traffic, if we look into the picture to the bottom right, there we see that out of the 65%, for example, in Southern Africa, 48 is BitTorrent, or in Eastern Europe, out of 69% of peer-to-peer traffic, 80% is BitTorrent. In Germany, BitTorrent traffic makes up to 70% in peer-to-peer traffic. So peer-to-peer is dominating in the internet traffic, and BitTorrent is the dominating application, peer-to-peer application that generates the traffic. So there's a lot of traffic going on, and the internet service providers, like it's in the title, they are unhappy about it. So the problems are that, for example, Tit4Tat optimizes for low download times. That's good for the users, but it's bad for the internet service providers, as the chunks travel all over the world and generate all over the world lots of traffic. So it would be much better for them to have only local exchange of data. Best would be if T-Online users would only communicate with T-Online users, and Vodafone users would communicate only with Vodafone users, so that the traffic would stay in their domain. But what happens is that it's really global traffic, and it generates inter-ISP traffic, and that's costly for them. So the idea and the motivation for the internet service providers is to somehow reduce those traffic. So what do? They filter peer-to-peer traffic to give them bad quality, bad download times, and that should keep the users off and minimize their traffic. However, this is also a very interesting point because it's harming the network neutrality. So it is somehow a rule that the traffic in the network should be treated equally. This is an agreement in the internet, and the internet service providers are very much willing to break these rules and to introduce some kind of differentiated services so that you pay differently for different kind of traffic. So peer-to-peer should be, for example, more expensive and slower, get bad quality than, for example, some more preferred traffic. So what could also be done is to integrate these differentiated services at the user level, to not anymore have flat rates, unlimited flat rates with unlimited bandwidth and unlimited volume. But as you also see in the mobile internet connections that are offered nowadays, you only get either fair flat, that is throttled up from a specific volume, or you also only have volume-based flat rates, so up to 300 megabytes, for example, you get you can use it up and then it's done. So the ISPs are not anymore willing to give you as much as you want, so you have to pay for it. What you can also do, and the ISPs could do, is to cache the peer-to-peer content. So as they know, okay, that some popular items might be requested from outside of their domain, they might create a cache for the case that this popular item might be requested later on, so they don't have to send out a request from far and have this inter-ISP traffic. So caching is the point. What they also tried to introduce is some cooperation. They wanted that ISPs cooperate with the application providers. So one term to memorize there is P4P, for example, a provider portal for applications. And the idea there is that you give some sense to the peer-to-peer application what is a good choice and what's a bad choice about peer selection. For example, in the BitTorrent protocol step 3, that was when the peers contact the tracker to request the peer list and to get information about which are possible contacts. In this step, the peer requests the peer list, but the tracker filters the peer list before. So it contacts the P4P server to basically rank the peers in the list to say this is a good peer, this is more in the domain of the requesting node, and far away nodes that are bad peers, they shouldn't be chosen. So to have some localized peer list which prefers nodes from the same ISP. So this localized peer list would then help to reduce the inter-ISP traffic. So what is the big goal and what should be achieved is to have chunk providers from the same or near ISPs to limit the inter-ISP traffic, to have peer-to-peer traffic remaining in the same ISP network, to lower the costs of the ISPs. But as a drawback, so just imagine that for every file that you download, you get a peer list which has been filtered by some server. That means that they can track what you are interested in, what you are downloading, and this is not very interesting for the user at the end. And it's also problematic because just if you think of tit for tat, it's really optimizing for the download speed. If we have now a localized peer list, this is some reordering in comparison to the optimal download according to the list with the optimal download rates. So it can only be worse than the previous solution in terms of quality. So ISP and traffic localization is interesting for the ISPs, but probably not for the peer-to-peer users. So what is currently also up to date? So what is currently happening in the network? So we saw that peer-to-peer is very dominant, but there's also a shift of trends. So peer-to-peer was dominant, but now it's going slightly back, and we are getting more and more multimedia streaming basically as main application in the internet. So what we have is we have more and more PC users, of course, more internet devices, and we are shifting from web pages and pictures to software and video content. So here's some overview how the numbers changed from 2007 to 2008, also from IPOC, and they found, so for different kinds of parts of the world, and what they found out, peer-to-peer got worse, so it's less used. What is used more? So in Germany at least it's the web. In Middle East, streaming. So streaming is not only in the Middle East booming, but also if you look at numbers from USA with Netflix or Hulu, where you can really download and stream movies and series, episodes, TV episodes, and this is going to dominate. So we are getting anyway more and more internet traffic and more and more servers, and it's anyway growing nowadays, and it's getting a problem for the quality of content delivery. So what they introduced and what they really want to do is to have basically, if you want to provide some high quality streaming, you want to send out your websites very quickly, and you are a big company like Amazon or YouTube or whatever, then you cannot have only one single server farm, probably located in the US, because then the users from Asia would be too slow in contacting that server farm. So what has been introduced in the last 5 years is so-called content delivery networks. So those you can think of some distributed caches in the internet, and you can rent them if you are some company and have some money to host your content. So here you can see some little picture for it. So from the operator side, from the big companies, for example, they have some movies that they want to share, and they have their server farms for it. And then they rent some of the caches in this content delivery network in order to deploy their content on those. And this is, for example, in Asia, this is in Africa, this is in Europe. Of course, you might have 1,000 of those nodes, so that it's very quickly reachable. And if the users now want to have the content, their lookup, basically their server request, is redirected to the closest content delivery node. And this node is then answering from its cache, and if it doesn't have, okay, then you have to go the long way, but typically it should have it in the cache. So what is considered is the user location and the network conditions. And the aim for the content delivery networks is to really have the fastest response time and a high download speed. So some examples. One of the examples is Akamai. Akamai is a company which was focusing on this topic since very early times, and what they have is they have several single servers distributed around the world. So they have a high number of servers, but only few servers per location. And some other company, Limelight, they have few data centers, but they are at strategic positions. So for example, if you look at the internet topology, there you have some central hubs where the traffic comes together. So for example, in Germany, around Frankfurt, there's the international hub. And if you place your data centers close to those locations, then you can make sure that, for example, the users in Germany are quickly served by the content they want to have. Yeah, what you have, so you have faster response time, you have less transit traffic, because the traffic and the content resolution stays basically in one country and one domain, and you can better load balance. So if you have a flash crowd, so lots of users requesting the content from one specific site, so for example in Germany, then you can also rent dynamically more caches to support those requests, and you can still make sure that the requests are responded in a specific time, so that the users are happy. So the trend, what should summarize these content distribution networks, is if you think of some kind of server farms, then you shouldn't think of some centrally, locally placed server farms where all the content is hosted, but you should think of also that kind of content hosting is distributed over the world, typically over hosts and in a hierarchical system. So the hierarchy is coming from, you have the rented content distribution network, and those request the content if they don't have it. So there's a second layer of it. So the drawback, so what it brings you is basically the quality of service. The users are happy and the providers are happy because they are able to provide good quality of service, but of course you have to pay for it. You have to rent this service, you have to maintain them, you have bandwidth costs, and you have also the problem if too many nodes are redirected to the same content distribution network node, then you might also have some overflow and some overloaded nodes. But at least here you can redirect the requests and you can adapt to it. So there are some similarities to peer-to-peer, and that's why content distribution networks are presented. So what you have in peer-to-peer is, on one side you have no infrastructure costs, and of course your supplies, what kind of resources you have at hand, grows linearly with the demand. You have simple algorithms, so it's somehow working, but you don't have these quality of service. You don't have the guarantees that you really get the response time within below some specific threshold. So if you request some content, you don't have the guarantee that it will be received within 1 second, for example. With content delivery networks, that's somehow more applying the ideas of these distributed networks on the server level. And what you have there is you have the infrastructure costs, but you might apply some centralized scheduling algorithm to optimize the load distribution on those networks and on those nodes, and their direction policies, so which node should be contacted by which users, that you can take effect on. What you also have is you can optimize the network inter-domain traffic basically and reduce it, and you can introduce some quality of service guarantees. So you can really define that some content delivery should be within 1 second or 2 seconds. Okay, now the question is, as it's somehow natural. So on one side we have the central infrastructure with the content distribution networks. That's quite popular nowadays in distributing content. And on the other side we have the peer-to-peer network, which comes for free but doesn't provide guarantees. So the question is, can they be somehow combined, ideally to have reduced costs but still a high quality of service? And the idea is, why should it be done? Okay, so we could reduce the load on the content distribution networks to have as least traffic in the content distribution networks as possible, to have lower costs. And so therefore we could use somehow peers to assist the content distribution network. And on the other side, we could use the content distribution network to assist peer-to-peer. In that case, we would use all the time peer-to-peer, and only if somehow the quality of service is going to be harmed, then we step back and take the content distribution network as a solution. So the question is, we will see how this could be combined and what kind of approaches there might exist. Okay, so with regard to the peer-assisted content distribution network, this is some simulation which has been trying to combine it. So the red lines are basically showing the users served by peers, and the green lines are showing the users served by content distribution networks. And here you can see, for example, if you take the peak, that would be the user request rate, and you see that half of the traffic and half of the load is basically can be covered by peer-to-peer, and with that you have also lower costs. So that might work well with popular content. So if you can somehow use peer-to-peer to redistribute popular content, then you can really use a wide set of peers to upload and download data. You have many resources at hand that you can use. If you have unpopular content, then it's very likely that only one node has the content, and it's getting very bad and slow, and you don't reach the quality of service requirements. One problem what is anywhere there in the peer-to-peer world is that you have this asymmetric user bandwidth. So your upload bandwidth is typically only 1/8 of your download bandwidth, and if you want to serve one user with full download speed, then you would require 8 users which only stream to that single node. So typically don't have so many uploaders, and that's why the content distribution network has to fill the bandwidth gap. What's also difficult is that you cannot use the typical protocols for streaming like HTTP or FTP to have this transparency, so that the application itself is unaware where the content is coming from. So if you try to combine different protocols, then it's getting difficult to make it really transparent for the application, so that it's just out of the box So typical and special protocols has to be applied. But still, there are some examples where this is done. So, for example, yeah, the Blizzard's World of Warcraft patches are distributed both with content distribution networks, but also with peer-to-peer assistance. So the users start downloading it from the website, over the content distribution networks, and as it is assumed that it's a very popular content, also the other downloaders are used to share the chunks of the patches. There's been also an application called BBC iPlayer, which applied this idea, and it was basically the idea to give the content of the BBC, of the TV broadcasting channel, free for the content of the last week to the UK residents, and it was heavily used and generating lots of content. But it was showing that this peer-to-peer assisted content distribution networks are quite well working. Okay, if one really wants to try to combine it, and this is one of the recent research points in peer-to-peer research nowadays, one could think of how can it be done. So the main idea is, of course, if nobody has the content in the peer-to-peer network, then we take it from the server. If somebody has it in the peer-to-peer network, we try to get it from the peer-to-peer network. So what are the requirements? We want to have fast downloads. Anyway, that's the most critical point for the users. It should be mainly from the overlay, so from the peer-to-peer network. Low distribution costs. That means, of course, this internet ISP traffic should be minimized, and it should be scalable. So if new users come to the game and also new content comes to the network. So typical challenges again, so no centralized control, no global information, and voluntary participation of the peers, and we cannot trust them, we cannot rely on them. So let's see how it can be done. So typically in this peer-to-peer content delivery mixture, you use the peer-to-peer as some caching overlay. And first, the files are only initially stored on the content provider servers. They are the main hosts, and they are downloaded from them and cached later on. When new peers try to download then the content, so what you only have to do is to find out, do other nodes have that content? So I could initiate and start some BitTorrent-like download scheme, or if not, if I cannot use the caches of the other peers, then I have to get it from the content delivery server. Yes, I think that's the same. So the main point, and that's not only limited to video streaming, but you can also think of how this idea can be advanced to some other typical examples. So the latest best paper award at the IEEE peer-to-peer conference won with the topic of how Dilbert comics can, for example, be cached and redistributed instead of using always the server. So the trend is heavily going to reusing the caches of the peers for content distribution. So movies, Dilbert comics, or whatever. So what is the approach? So here you see the server in the middle who has the main content. The clouds are depicting the ISP domain. So this is, for example, Vodafone, and this is Telecom, and this is something else. And if one node is looking for the content, and the content is located in, for example, these networks, then he could send out some queries. So either use a protocol like you have an overlay, it's like a DHT, in which you can really search for content and look for content, and then download it from it, and then you have the content yourself, and if somebody else is asking, then you also get the content. So at the end, you could simply apply the overlay techniques that we saw in the first lectures. So if having a DHT, then you can really start a lookup for the content. Or you could also apply some tracker-like system. So if the main content host is implementing, for example, a BitTorrent tracker for its content, and if the peer list is too small, then it could just simply serve as a server. And if the peer list is filled, then it's not used. So you can easily basically combine the BitTorrent protocol with the content distribution that you have in the internet with typical servers. Yes, okay. Another point is just assume you use the peers as caches, and you apply the BitTorrent protocol, which has both the leechers and the seeders, and once you downloaded the whole content, you become a seeder. And the question is, how long do these peers stay online after they have the content? So just assume you looked the YouTube video and you retrieved it from, for example, other peers, and now you have also this YouTube video in your cache. So you might leave the network immediately. This might be your default configuration, so that you do not want to seed anymore, and you might stay online and continue to seed. So what would be the effect? And it was also simulated. So here you have the download time, for example, number of peers who have finished. So with their download status is basically here, and here you see basically how the number of peers which finish their download, after which time. So if you leave directly, so leaving probability is 1, then the peers finish basically their download time after 120, 130 seconds. But if they would stay online, then the download speed is reduced by 25%. So over all peers, the download time is 25% less. Of course, some of the peers might be faster or slower finished, but for the whole network and for the whole swarm, it's more beneficiary if the nodes stay online. So, and the caches could be really treated as additional seeds. So if you download the content and you keep it in your cache and you participate in the BitTorrent protocol to redistribute it, then you have this already proven efficient mechanism to help other peers to get the data. So the question is which swarms to join, how much to contribute, and how to make sure that the download rate and delay are somehow matched, that are required. Okay, so for the last point, that's what I'm going to present next. So if you think of some larger movie that you want to stream, and it would be very nice, of course, if you get it from a server in a good quality, but for the provider it would be very good if he could reduce his traffic load. So video streaming is a very, very popular topic anyways in the internet nowadays, because this is booming nowadays. And the question is, how can peer-to-peer become so good in its quality that it's always providing a good quality? So good quality of service, no delays, no interruptions, and a quick startup of the video. On the one side, so good quality, and low costs, so no costs at all for the provider because using peer-to-peer. And there the topic of adaptive peer-to-peer live streaming is what is basically the big research field nowadays. So summarizingly, okay, peer-to-peer streaming and live streaming at all has become increasingly popular, and there are many receivers, many programs. Just think of IPTV. So PP Live is very prominent, I think, in China. So Satu has been popular no, it's still popular. So you can watch German and German, so TV, broadcast TV channels from German-speaking countries. Subcast is also some IPTV, and it's all peer-to-peer based. You just have to install the program, and you can pick the channels. And what you want as a user basically is to have the image appearing quickly and no interruptions later on. So how can this be done? So there are two ways which we will have a look at. So you might have a tree-based overlay that you can think of some multicast tree. So where the content is pushed down the tree and the receivers and the recipients are at the leaves of the tree and they are getting the content at some time. And every node in the tree might, for example, have 3 to 5 children according to the bandwidth he has available, so that the content is pushed. The other point is more inspired by BitTorrent, where you have a mesh or a simple graph or whatever you can think of, where you pull the content depending on what you would like to have. So this is very similar to BitTorrent, only you do not take the rarest first, but most prominently the chunks that you would like to have next to play your video. Question and that arises there, how to create those topologies, how should they look like, and how can we somehow guarantee the quality of service? So how to make sure that the startup time is quick and interruptions are very rare. Here's the applications that are already using it. So the BBC iPlayer, I already said, that was some application which was tested, I think 2 years ago, and the idea was to give the content of the last week of the British broadcast channel free for the residents of the UK. So it has an IP filtering to limit it to the UK, and you could download and watch episodes that were in the last week. And it was generating, so it was only used, I think, for 5,000 users or 10,000 users to test it, and they were generating so much traffic that if they would have deployed it for the whole UK, it would have consumed all the available bandwidth in the backbone. So very prominent, but too prominent to deploy really. Yes, so and the main idea was to have this streaming. Of course, they introduced all these copy protection schemes so that you cannot download it, you cannot save the content, you can only stream it, so watch it. Hundreds of users, so up to 5,000. It was stable, everything was fine, and it was too prominent, too successful, so they didn't really apply it because that would have generated too much traffic load in the network of the UK. Octoshape is another provider. They were applied and used. So just say what they did. So what you have there is you have some servers which initially introduce the content to the peer swarm, and they exchange then later on the content. So it's yeah, a little bit like BitTorrent, but more centrally organized. And it was used in for streaming the Eurovision Song Contest 2006 with 140 viewers from 140 countries, with a quite high quality stream. And they claimed that due to this peer-to-peer exchange protocol that was implemented, they could minimize the traffic consumption to 3%, so traffic savings of 97%. And how did it work? Just to give you an idea, so you had to install a browser plugin which was taking then care to redistribute the content. So it's still used, I think, also in the Eurovision Song Contest 2007, but it's also not clear, so they are also hiding somehow the protocol which they used, because I mean that's a company, that's their profit to keep it secret. And Satu is an application that you can also try out. It's very nice. So you can see how it works. So you have channels, you have a TV window, and you can, I mean, it's streaming TV channels on a peer-to-peer basis. So how does it work? So what kind of approaches exist to implement these kind of streaming? On one side, like I said, you have the tree-based video streaming, where you have at the top of the tree basically the server, the source of the content, and yeah, every peer receives the video stream from its parent. And here it is a binary tree, but of course you could adapt the tree structure to the capabilities of the tree of the nodes. So every node should have peers according to his bandwidth capacity. So if he has a very high uploads capacity, then of course he could bear more peers as children. And if he has less, then he might be a leaf or have only very few peers. So very simple idea and to visualize. Of course, it's good on one side because you can somehow control the tree. You can also take effect from the server on the structure of the tree. So, and the tree size is typically logarithmic. So you have a high efficiency, low delay, no retransmissions. Every node is getting only the content that he's requiring to have. But what you also see, of course, on one side, resilience is a problem. So if one of the nodes fails, so for example, that node fails, then the subtree is cut off and you have to rearrange a tree. Then you have some interruptions. You have to make sure that these interruptions don't take a bad effect. Can be done, okay. But what you also see, and what also is a problem, is that the leaf nodes are not uploading at all. So half, and typically as this is the logarithmic size, you have half of the nodes as leaf nodes, and they are not contributing anything to the system. And that might be some waste of resources. So the other approach is very similar to BitTorrent. So every peer uploads and downloads content from each other. But what you don't have now is you don't take the rarest first policy to pick the chunks, so which parts of the video stream you want to have, but you pick it according to your playback position, basically. So we will also have some slides for it, but why is it good? It's more resilient to churn, so any node might leave the network, so you don't have this critical nodes anymore. And upload requirements are flexible, so every node might also upload and will have to upload. Cons, the drawbacks, of course, might have redundant chunks, so you retrieve and redistribute chunks that are already very prominent in the network, and you cannot really take effect on it. Also, the efficiency is lower because you don't have that strict arrangement of the nodes, so that the strongest peers are basically at the higher levels of the tree that are pushing down the content. But you have also you cannot optimize basically the topology like you can do it in the tree. And you might also have a high delay because you do not only exchange the chunks and the video parts, but also your buffer maps and how far you are, what you want to have, which chunks, what you offer. So you also use up some bandwidth for those signaling. Okay, how does it look like? So every node has basically, so these are single nodes, and this is an example buffer map, and the blue parts are those chunks which are already received, and let's say here's the playback position, and you want to have basically always the chunk close to it filled because it's a queue and it's used up in that direction. So you always want to have basically the chunks which you have to play back next. And those buffer maps, so what kind of chunks you have, that you have to exchange periodically, like you also have to do it in BitTorrent, where you signal to the tracker what kind of content you have. So now the block or the chunk selection, in contrast to BitTorrent, where it is important to keep the rarest chunk in the network so that it doesn't get lost. Here it is important that you do not interrupt your playback. So that means you always have the chunks that you will have to play back next. So if this is the playing window, so you're currently, for example, here, and this is the timeline, so in the future you will need those chunks. Now and the blue ones you have and the red ones you don't have. What you want to retrieve next is basically some of the chunks from, so these chunks you should have, so they have highest priority. These have medium priority basically, so it doesn't matter whether you get the second one or the fifth one. So you won't have one of the chunks from there, but with highest speed. And the chunks that are far away from the time, they have low priority. It's okay to get them if you have a high bandwidth peer as a contact partner, but it's not so important. So you're more looking to get chunks from your buffering window. So, and because you have a window from which you can choose chunks, basically, you can still choose in this window the chunk which you can get fastest, basically. There you can still go for high download speed. So you still download from multiple peers, and yeah, there you can optimize your download performance. Here it is again pointed, so you have the high priority set. So anyway, in the playing window, that has the highest priority. So if something is missing there, you retrieve that chunk. Then you have the buffer window, that's the high priority set. There you use the one closest to the playback position. So it's close to the playback position, and but still it's a set, so you can optimize in there. And you have a low priority zone which are not so important, but soon will be important. Okay, and so this is basically the idea of the mesh-based video streaming in a peer-to-peer network. And now we want to go a step further. So this kind of BitTorrent modification where we only modify the chunk selection, that's okay. But what we also want to have is to really have some support for both quality of service, so the interruption times are low and the startup time is fast. And what we also want to have is to have a support for weak peers and strong peers, so that means heterogeneity. And there comes into play this adaptive video streaming. So here another measurement and some prediction how the traffic will evolve. Of course, this is just guessing, but it is said that video streaming is going to explode. And typically, if you look at some research papers, every community say their research will explode in the future. It will be most prominent. So this is from some video streaming community that are predicting this trend. Okay, let's assume that will happen, and we will have internet video on PC and TV getting this big impact in the internet. What we have still going to have is we have a heterogeneous network. So we have home PCs, we have netbooks, we have smartphones, tab PCs, whatever, with different capabilities, bandwidth, screen size, CPU. And we all want to support those all, basically. Of course, on the user side, we want to support them all. On the provider side, we want to reduce the server load and make it very cheap. So we want to use peer-to-peer basically. So how can both the peer-to-peer approach match to those heterogeneous nodes? And this is really some problem also of BitTorrent, where you only have basically one file and one video stream that you redistribute, and it doesn't match really, for example, all the devices. So what you, for example, also see, if the video has this resolution, so 1920 times 1080, you cannot display it anyway on your smartphone, and it's not clever to retrieve the big video if you cannot display it. So it would be better to have some smaller resolution, for example. Or if you have anyway a smaller, let's assume you are connected via UMTS with your home PC, you have the resolution, but you don't have the bandwidth to transfer it. So then you would also like to have some adaptive video streaming. So that it adapts to your user device and your capabilities and only displays for it the best quality, basically. And there the scalable video coding comes into play, which is currently, so it has been standardized 2 years ago, and is now taking somehow effect. So what is the scalable video coding? What is adaptive video streaming? So just assume, just as a background, what you have is, if you have again, motivation client server that's only scalable for low resolution content. So if you have a look at YouTube, for example, you can choose your resolution, so 702p up to or down to 360 or something, and you can choose the resolution. It's also adapting, so it's changing the resolution on runtime, but you might still have some buffering time and some stalls, and so it's only adaptive in the resolution. Peer-to-peer, of course, if enough peers are online, everything is possible. That's always the claim. And now the idea with this adaptive video streaming is that you have a multi-layer codec, so that H264 advanced video codec, and where you have different layers. And this is basically a visualization of one picture fragment, let's say. So you have a base layer which contains the minimum information about the picture, like colors, low resolution, and many artifacts. And with every block that you might retrieve later on, or additionally, you can improve the quality of your picture. So I think the picture is a little bit misleading, because you could think of every block has the same size. What it should visualize is, if you have the base layer, you can put additional blocks on it to improve your picture, and there you can put also more additional blocks on it. So the more you retrieve for a specific picture or a specific video playback time, the more blocks you retrieve for it, the better the quality gets. That's the magic, basically. And all the blocks have the same size. That's not well done, but that should be the idea. And the idea is basically, if you have only very small bandwidth, then you only get the base layer. If you have more bandwidth, then you get more blocks and improve the quality. If you have much more bandwidth, you can get more blocks to improve it. You can also choose to only get the blocks for your resolution. You can only choose to get the blocks for we will see the examples, but I think you get the idea. Yes. What's also done, so for this adaptive video streaming over peer-to-peer, so on one side you have an adaptive video streaming codec, and you have underlay overlay construction. So you can also adapt and create the overlay structure for the nodes in which they exchange the content, aware for delay, for locality, for bandwidth, and you can optimize for that. So both aspects we'll have a look at. Yes, so I think it's clearer in this case with the blocks. So this is the scalable video coding block, and that you can model as three-dimensional cube. And the dimensions are signal noise ratio. That means how many artifacts you have in your picture. So if it's very high, then it's very clear and sharp, the picture, for example. If it's very low, so the noise is very high, then you have many artifacts and compression artifacts and all that. So this is the compression. Then you have the temporal resolution. This is the number of frames per second. So you might also be happy with 10 frames per second or 5 frames per second if your bandwidth is low. And the spatial resolution, this is the resolution of the picture. So whether you have 480 times 320 or you have high definition or whatever. And as you also can see is that the base layer is available in of course all dimensions, and you can extend the content that you retrieve in any directions. So for example, if you have a device that is capable of displaying high definition pictures, so very nice monitor, then you can go up basically in the dimension of the spatial resolution. If you want to have also more frames per second, then you go to the right. If you are not able to display high definition video, then you, for example, just improve the compression ratio bit. That means to have less compression and more frames, but no spatial resolution. So you can pick which kind of information you want to add to improve your picture. And what should be known, of course, interdependencies of blocks. You also have some deadlines for the blocks, because this is only for one time frame, basically a block. And if you retrieve it behind your playback time, then it's useless. And of course, user preference. So you can pick the kind of blocks that fit to your device. Here are some examples. Yes, the temporal scalability is of frames per second. For example, for mobile phones, you would pick less. Why is iPhone not a mobile phone? Okay, so iPhones and of course Android phones, which are better, and PCs. There you can choose even more frames per second. The spatial scalability, that's the resolution. Here should be also named high definition. So there you can also vary, and these are so here you see the resolutions and the compression of the pictures. So if you have a very extreme high compression rate, then you have these JPEG artifacts, for example, and although you have high resolution, you might see those artifacts. So we can adapt the picture in various terms. Now, when do we adapt? That's the question. And there you have two types. First, the initial adaptation that you do when starting the video. Then you check, okay, what kind of capabilities do I have? And start retrieving the content with that kind of quality I measured. And you can also have progressive adaptation. That means to change the picture and the video during the runtime, independence of your bandwidth, your delay, whatever you have, that you can do periodically. So both adaptation types exist. How's the approach? Yeah, that's what I said now. So you start with an initial adaptation, check what your peer resources are, your network capabilities, and then you come out with some setup, basically, which quality level you want to have. Then you go for the chunk and block selection. That means so the chunks, these were the time slices for the video, and the blocks, those were for a single time slice, basically these scalable video coding blocks with the temporal and spatial and signal to noise ratio blocks. And then you stream it. And what you also might do is periodically adapt the quality level due to according to your new characteristics, basically. So how is then the initial quality adaptation done? As I said, it is aiming at coming out with some initial quality level that you start downloading on your peer resources. That's what's considered. It's done at the beginning of the video playback, and then this is basically how you go through. you first pick your screen resolution. So you would go for the best, basically. It's of course depending on your device. Then you check your available bandwidth and pick basically the frames per second. So how many packets you want to have per second, how much you can take, and then you also check the compression, what you can take into account. So if you have higher processing power, then you could also take compression rates which require more time to decompress but have better quality. And a progressive quality adaptation, that can be done periodically, every t seconds, for example, 5 or 30 seconds, for example. And there you consider always your current network status. So not anymore your screen resolution, because that you knew already. So for example, how well blocks are available, how your throughput is, how your processing power is. And the idea is, and the goal is to hinder the network, the video stream from being stopped because blocks are missing, for example. So these are the so-called stalls, the interruptions in the video that you want to avoid because it's most annoying to the user. Yes, and how do you avoid these interruptions? You switch temporarily the layer to a lower one so that the video is still continuing, still running, but in a lower quality. And if you identify later on that your capabilities are high again, then you switch back. Okay. Yeah, that's what you adapt. So you check your net status to modify basically the temporal resolution, so the frame rate. Then, I mean, you can again do the same aspects that you adapt. So what can you adapt for? So you can adapt for the network status. So you check your bandwidth, and you request only layers that are available within your local neighborhood. So basically there you check what your contact nodes, what kind of chunks they have, and what's the highest supported scalable video coding layer. What you do not want to do is to wait for rare blocks. So if you see that in your neighborhood some specific block that you would need to keep up the quality of your stream is missing, then you do not start searching for the block, but you just miss it and you switch your quality back for a short time. So that's one approach. Then you have the bit rate adaptation. There you basically go for your highest priority set. So that means what is your time slices and blocks that you want to retrieve next, your chunks that you want to retrieve next, and you pick the ones which have the highest throughput, basically. Of course, you can check for the whole priority set how the throughput is, and what you want to do is to avoid this buffer underrun, and also there you switch back. So if you don't have enough throughput, but you want to have this high priority set, and you can't get all of it, then you switch one quality back so that it's still running. Okay, and of course, if you don't have enough processing power to decode each layer, every block, so if you cannot, if you can't do it in time to present the picture, then you skip the decoding, and there you also go some step back. And you have a picture with more artifacts, more compression fragments, because you couldn't decode it. Okay, so what are the aspects, the protocol aspects that need to be done? So you have a tracker that is managing both the peers. That here you have again the similarity to BitTorrent. So also here you have a tracker that keeps an eye on which are the active peers, which chunks they have, and which layers they have. And It helps them, of course, to find each other and to find nodes which have the same, which offer chunks that the other nodes are looking for in the same layer type. And you can use those trackers to advertise your chunks that you have and the layers that you have. So yeah, so they advertise what they have, and they also, after the adaptation, they tell the tracker what they have and what they want, and it's very similar to BitTorrent. So also, yeah, the buffer maps, which were previously one-dimensional, only storing the chunks which are going to be played, they are also now containing the information about which layers one node has and what one node wants. So just an extension of this old BitTorrent protocol with the information about the layers per chunks. Okay, and what comes out at the end is that the peers cluster according to their resources. Of course, the very strong nodes, which have the layers, all the layers, basically the highest quality, they are also serving the nodes which are capable to display the highest quality. But they are not limited to those. Also, the weak peers can help, and also so that's not limited to these classes of strong or weak peers, but they can also help each other. Okay, so why is this all done, and when is a solution a good solution? So there are some evaluation metrics for video streaming that is generally important. So it's not depending on one solution or one approach to decide whether some protocol is good or not, but it's usable for any kind of streaming mechanism. And the first metric that is relevant is for the session quality is the relative playback delay. There you take the whole playback time and you count the startup delay. So that means how long did you have to wait until the video starts, and summing up all the interruptions in between. So how long did it take? So what you don't want to see is basically the buffering symbol. That's to minimize. So the relative delay is thus the waiting time in comparison to the whole playback time. Also the video quality. What you also want to minimize, what is bad, is the number of layer changes. So although it's good to change the layer to support so you change the layer to minimize basically the interruptions, but these changes are also not very nice to the user. So if you think of you're watching a movie and it's jumping every 3 seconds in its resolution or in its compression ratio, then it's somehow annoying. You would be happier if it stays with a lower resolution for a minute, for example, and then it jumps back, so the jumps are rare, instead of always displaying you the best quality but having many layer changes. What you also want to measure is the relative received layer. That means out of the available layers that I could have, which quality did I really retrieve? And yeah, that's said. So less layer changes or higher relative received layer. So if I get the best quality I can get, then I'm happy, and if I'm having less changes, then I'm also happy. Yeah. So these are the two metrics that are relevant. And here's some simulation which just shows how the initial quality adaptation, the progressive quality adaptation, affects the quality of the weak peers, medium peers, and strong peers. So on the x-axis you have the weak peers up to 30, then the medium peers in this range, and the strong peers. And the blue points are depicting the total playback delay for a movie without any adaptation. So the weak peers have 200 seconds of buffering time, of interruptions, and they are very unhappy. And the medium peers, okay, we have some stronger peers which have to wait a long time, and some of them are having less interruptions, but still you have more than 100 seconds of interruptions, and only the strong peers have somehow a better quality if they get the highest quality from the beginning, but still they also have to wait and buffer. If you have the quality adaptation in the beginning, so that you initially adapt your quality to your resolution and your bandwidth capabilities, there we see that still, let's say half of the peers, 1/3 of the peers is happy, but 2/3 is getting some interruptions up to 60 seconds, and also with the medium and strong peers. So they all have to wait in displaying the video. And if you have the progressive quality adaptation also during the runtime, so if your network capabilities change and you adapt, then we see that the number and the delay in seconds is below 5 seconds for the weak and medium peers and below 10 seconds for the strong peers. So they are getting happy because you get the video stream according to your device capabilities. And this is also working. This is another picture showing how the progressive quality adaptation takes effect if you make it every 5 seconds and every 30 seconds. Here you see the changes are less frequent, although you might have more white spaces, and if you make it every 5 seconds, then it's probably too annoying for the user to have the changes. So for example, let's take a picture, this one, so it has a low buffer state, so it changes, and then to a lower quality, then it has a full buffer, then changes here every 5 seconds in this time or over there. So the user might get somehow annoyed with the quality changes. It's probably better to have it only every 30 seconds. Okay, so summarizingly, what are the main questions in adaptive and or peer-to-peer streaming at all? So this is the big questions that if you want to create a streaming protocol have to solve. First of all, okay, the content is somewhere out there, but how do I find and select the peers that provide the content? So which peers do I take into my peer list, with whom I want to exchange chunks or video parts? From which peers to retrieve a chunk? How do I coordinate the chunk exchange? So the first question was from whom to retrieve, and the second is whom to give, basically. And do I apply the tit for tat strategy or what else? Then picking, already knowing which peers I will communicate with, which chunks do I select? There's a typo. So which chunks do I select from those peers? So do I take the rarest first? Do I take the next one in my playback time? So which chunks to request and to give? How to behave with unpredictable variations in bandwidth? If it's changing quickly and if I missed some playback time, what do I do, and how do I prevent missing the playback time? And how do I assign the packets to the nodes? So which peers do I select for it, depending on the network and root status that I get from it? Okay, so summarizing, so peer-to-peer video streaming is, of course, going to have a big impact, as video streaming is going to have a big impact, and also these heterogeneous devices are coming up, and what we want to have at the end is to have videos everywhere, any kind of content, any kind of TV shows on our PC, on our mobile phone, depending on the bandwidth that we have, and scalable video codec is supporting it basically by you are able to adapt what you retrieve to your capabilities so that you always have the best quality for the device that you have. Okay, and how this adaptation is basically done, there are also some advanced approaches so that you pick the quality level of your video stream in the beginning and progressively on the periodically, and everything is taken into account also, yeah, how the different aspects, so the bandwidth and the computational time and all this is affecting the quality of the video. That can be all evaluated, and you can come up with some adaptation strategy that really makes sure that your device is optimally used. What can be still varied and can be had a look at is what should be the optimal progressive quality adaptation interval, 5 seconds, 30 seconds, 1 minute. Does it also vary? That's unclear. Some prediction-based layer selection, so that you can somehow, it would be ideally if you would know how in future your quality will be and your capabilities will be, so that you can already retrieve that kind of quality to show later on. And what should also be done is to always integrate the quality of the experience. That means the user feedback, whether he's happy or not. So if the user would say too many quality adaptations are not well suited for me, I don't like it, then you should also adapt it in your protocol. Okay, so this was the overview to adaptive video streaming. Now the remaining of the lecture will be on one very prominent peer-to-peer based video streaming project. And this is the largest European peer-to-peer research project. It's called Peer-to-Peer Next. It's funded with 20 million euros. It probably doesn't look so big, but it's from research point of view very much money. So this is hosted at the TU Delft in Netherlands, and they are implementing and researching a protocol called Tribler. And what they want to do is to, let's say, previously to this project, BitTorrent was BitTorrent and only for file sharing, and they wanted to extend it to real video streaming and make it applicable and make it usable and investigate all the little details that are hindering the success of peer-to-peer video streaming. So it was first released in March 2006, and up to now at least 1 million downloads, so it's still used. And there's also they are also having some contacts to Wikipedia, so that it should be extending Wikipedia, that you can stream also videos and then display some videos in Wikipedia. So that's basically where their research will be applied soon. So what they do, of course, first of all, BitTorrent-like file sharing, that's somehow still a must, but also video streaming, and there should be more research applicable in the area of peer-to-peer if this is once distributed. So also this following slides are from the professor who's managing the project, which I met half a year ago or so. Okay, so it is also the Swarm player. This is basically the video streaming is also used in Wikipedia. I found it sometimes that you can really in the Wikimedia watch some videos, but it's not that prominently distributed. What they also do is to have this Swarm player in Pioneer set-top boxes. So this is also some research field. If you think of your set-top boxes for broadcast channel television receiving, there you could also install some kind of BitTorrent application on, and that you can use to redistribute the content. Yeah, and you have also a user base from 5 to 10,000 users all the time. So it's still somehow successful. So what it does, and what is the main idea, is to consider the peers as actual users, and you also want to have some social functionality. So you also want to introduce some type of buddies, some friends with whom you prefer to share contact and content. Yes. And what else is included? So you have an epidemic protocol for peer and content discovery. So you do not rely too much on trackers, and you use a mega cache with information on the whole system, which contains where content is located, what the quality of the network is, and which helps. Later on, there was added, so this was the addition to BitTorrent, which they started with, and then later on, video on demand and live streaming, content discovery with keyword-based search that we also had how in some previous lecture how it can be done. You have channels which sort the content according to the user who injected it. Some reputation mechanism, so-called bartercast, which uses the friendships of the users. So the friends of the users are used to increase the download speed, basically, and also the web-based swarm player, which is then integrated into Wikipedia, for example. So, what is how is the overlay swarm looking like in Tribler? The main idea is to really take all nodes into account, and all nodes should be activated. And in contrast to BitTorrent, you don't have one single swarm per file, but you have a swarm with all nodes. So here you see the difference. So all nodes are involved instead of only. So in BitTorrent you have per file one swarm, and in this case it's all nodes included. And this swarm is used for peer and content discovery. Okay, so and how do you join the network? For that there's a bootstrap peer which is globally known. That might also change, but it's still known to the users. And this bootstrap peer is contacted first. It gives them some more information about the swarm so that the new node can join the swarm easily. Yes. Great. Okay. So that's a little bit like BitTorrent, but with one single swarm instead of smaller swarms. Okay. What is new? So BuddyCast is new, and this is having following effects. So BuddyCast is an epidemic protocol. What you want to do is to find peers and content that you are looking for and that you can recommend to others. So what every node does is he has a list of his buddies, his friends, basically, and of random peers. So yeah, here you can see how it might look like. So this is the main node. He knows his social network, his buddies, and so the guys with whom he likes to exchange content, and some other nodes which are exchanged more frequently. What you want to do is to basically create a cluster with nodes who have the same taste, so that if you are looking for content, it's more probable that you find the content in your social network than in some distant network. Yeah. Okay. So how do you use it? So first of all, how do you communicate with those nodes? You tell those nodes that you have in your contact list, both the random peers and your buddies, what your preferences are, what you like, who your buddies are, what your buddies like, and whom you know. So you make it quite prominent what your buddies have and what you want, and you don't try to hide it, but you want to give as much information of you as possible so that you can more easily create those clusters of with the buddies with the similar taste. The mega cache, what's also added, is the main idea is to both give information about the content in the network, but also about the network itself. So to give some context, so the network capabilities, your storage space, and this you epidemically disseminate, so you exchange with your neighbors what you have. Okay. What is done then is that you have the bodycast message, which you send out periodically, and what you want to achieve is to basically learn about the other nodes in the network, to identify nodes that have the same taste like you have. So you exchange with those nodes, you either the buddy or the random peer, you merge the buddy lists. And the idea is that with this merging, you get some more information about other nodes, and you might identify nodes with similar tastes. And the epidemic, why is it called epidemic? That's because you only exchange these networks with your neighbors. So like a epidemia, like a sickness, you only contact your neighbors and exchange information or viruses with them, and that's why it's epidemic. And with these epidemic protocols are very robust. I mean, every node has some neighbors, so it cannot really fail. And still it has the effect that the nodes learn the desired information about the network. They find nodes with similar tastes, and they can cluster. So why do we need the clustering? The clustering is motivated in order to enable this collaborative downloading. So previously in early peer-to-peer systems, what the users wanted to do, just download, nothing uploaded. So especially in Nutella, it was shown 70% of the users are only downloading and not uploading at all. With BitTorrent, they introduced the tit for tat. There you have to really give as much as you download. But you have the problem that you can still download more than you can upload, and you cannot somehow use the remaining download speed. What they wanted to implement with the so-called too fast algorithm in for Tribler is to also use up your download speed, although you cannot give more. So how is this done? Here again, the same example. So you have a peer with a download speed of 1024 kilobytes per second, but you can only upload 256. And this asymmetry is just given. You cannot change it. And with tit for tat, you can only have basically the same ratio incoming like outgoing. So you cannot also take an effect on that if you do not change the tit for tat protocol. And now with the too fast protocol, what they introduce is that you have so-called friends, which help you for free. So if the friend has somehow free upload capacities, he can contribute to you. So the idea is just you split the whole world in friends and no friends. If you don't, with the not friends, you only give what you get, and friends give for free. Just assuming that a friend is currently not downloading something so that he doesn't use his upload. This is the idea. And with it, you can increase the download performance up to really using it optimally. Yeah. Okay, so this is some evaluation how the effects are, and this is the so-called yes. So the red corner is the perfect speed up. So how this is the on the x-axis number of helpers, how many friends you have, the speed up in terms of how much faster you are. If you have no friends, then you stay where you are. and with at least five friends, you would have mathematically the maximum outcome. And if you don't use redundant chunks and no swarm information, so you do not have this epidemic protocol and you do not exchange this information with your neighbors, then you come only to double the quality. But if you take into account the redundant chunks and you inform your neighbors about what you have and what your friends have and what they offer, then you can come up to this perfect speed up. So it's really helping. Okay, so what is this Bartercast? Let me just... Okay, so what you want to have basically out of as an addition to BitTorrent and this video streaming is to identify who is giving how much to the network and who should be helped and who should not be helped. So what they want to prevent is this lazy free riding. So you really want to somehow introduce some recommendation which nodes are good and which are bad and which should be supported and which should not be supported. So what you should maintain and propagate to your neighbors is the history of your own data transactions that prove what you have done and the interactions among other peers, what you observed. So what you have seen, what others have done. And what you create then is, so these are the nodes, and you just display your knowledge about who helped whom. So here you are, and you helped, you sent some data to A, B, and C, and you received from A the information that he received some data to D and to E. So you just have a local view on the graph of who gave whom some content. And you can now exchange this information. So these are two local graphs. So the node 10 in this position has the local view on he received some data from node 9 and he sent something to 4 and he sent something to 12. And this is the local view of node 9 where content came from and where he forwarded it. And if you use this epidemic protocol, you exchange the information and you combine the local views, you can extend your local network, your local graph about what has happened. Basically, you get a bigger picture of the network. And with getting a bigger picture on the network, you here it's again the same how it is calculated. So you take both subgraphs and you calculate the max flow algorithm, and you can calculate between every two nodes who gave how much to whom, basically. So here a flow is in that direction, for example, and the flow is in this direction. So you can calculate for every two node how much the flow is, which was given in the previous time, basically. And with that, you can calculate the reputation of a peer with a given formula, and that tells you how trustworthy and how supportive this node is, how well he is, how active he is in the network. And with that information, you can decide of whom you want to help with your free bandwidth and whom you don't want to have help. Okay, so here's the calculation of the max flow, basically between these two nodes. And for the whole graph, it's too difficult, so that's why you reduce the hop count, and you just limit basically the size of your graph that you're considering, and you come up with the reputation. What you also have is your local peer might not be in the middle of the subjective local graph. Okay, and instead of full gossiping, you limit basically the gossiping. You only transfer the information what you have to one hop distance, but still everyone at the end has complete knowledge because you If you propagate it to your neighbors and they propagate it to their neighbors, with the end you get the information about all nodes, how well they were performing. Okay. So what is the outcome? So first of all, again, they did it in Tribler, and here the coverage is basically computed in comparison to the maximum flow length. And the point is, so what you want to have as an outcome is basically a full coverage, that would be best, and a small hop count. And if you use yes, so if you use it without, yes, so this is the coverage and this is the median of estimated error, so how wrong is the estimation. And although the coverage is small, in this case, the error is also small, and if you have a big coverage, then you have a small error. So you can still configure your size of the local graph to have a, probably you would prefer to stay here to have a middle error, but also a high coverage. Okay, so final words to Tribler. So what they said is they were trying to come up really with a solution that's working and that's used in the internet and people are happy about it. And they were also trying to promote it and to present it on some exhibitions. And what was the outcome? The outcome was first the observation: the market and the internet users in internet are only open to major products and technologies. So if you have only an idea and only a rough estimation how it might work and it still has some bugs, don't go to the market. Don't pretend that it's working. You shouldn't also make promises about new products or features that you cannot keep, and you are not sure whether that you can keep. And especially in the internet and the, let's say, innovative sector, you have only one shot. You can only present yourself once with a first picture, and if you fail, then you're basically out and you cannot improve it. So you have to come up with a very perfect solution that's meeting the needs of the users, and then you have success. And what you shouldn't also have is you shouldn't go too broad with your product. So you shouldn't have too many features, but rather focus on a few unique selling points. So my example here is always Doodle. So some of you might know the web page Doodle, where you can negotiate on some meeting times, for example. And they only offer this little service, but that's very good. And that's having success. That's also rated with several millions nowadays, I think. One single feature which is working and not a broad product which is not working. So with P2P file sharing, so what they still are aiming at is to have private-like performance in public communities. So if you would have a private peer-to-peer network with known friends and everybody's helping everybody, that would be very good, but it's not working public because they're not trusting each other. But still you would like to have the performance. So the quality of the offered content is also to be checked. So how can it be guaranteed that you don't have this pollution, that you don't have malicious content inside? The support of mobile nodes is also a point that they are aiming at. And also the integration of online social networks. If you would know that they are really your friends, you could help them in the in the file sharing application. But what is anyway the outcome of this biggest peer-to-peer project is, if you really want to make some progress and to have some impact with research, you have to make actual implementations and deployment. So you cannot do research on paper. You have to really implement it and test it, and there you see where the problems are. Okay, so this was the last slide of the section, and next time we will have a look at storage. So thank you very much, and don't forget,